All right, so as we look at chi-squared test, or chi-squared, this is the Greek symbol for chi, not chi and not chi. We use it to test for relationships of categorical data. There are three types. There's a goodness of fit. Univariate means one variable. Independence, which is a bivariate with one sample. That means two variables that we're comparing to each other. And then homogeneity is one variate with two samples. One variable, two samples. And so as we look at this, we notice the curves for chi-squared are skewed hard to the right. The tails run this way. They're flat here, they stop here. But as the degrees of freedom increases, the top of it drops such that not only is it skewed to the right, but as the degrees of freedom increase, it becomes more like a normal curve. Not necessarily a true normal curve, but it becomes more like hang on just a second, let me adjust that screen just a little bit. But it becomes more like a normal curve. And this is the equation. Chi-squared equals the sum of the observed minus the expected, quantity squared, remember we squared to get rid of negatives, divided by the expected. And this is on the formula page. Okay, this is written on your formula page. You should have that. And so we look at the back side of this. So the goodness of fit, which we're going to work with first here, uses a one variable data. We have the observed counts, and we fit what it expects to be. We're not going to use the CDF function. We're going to run the test. Okay, and so based on the degrees of freedom, which degrees of freedom is found by the number of categories minus one, so that's C minus one, we write our hypothesis in words. Okay, the normal thing is for us to say that proportions are the same, our expected numbers are the same as the observed numbers, but then our alternative is that at least one is not the same. And make sure we always write in context. Okay, which leads us to our conditions, and there's only three conditions, which is normal for us, no pun intended there. We have a reasonably random sample or a randomized experiment. Now, sometimes I'm going to add just a slight tweak to this. Sometimes if it's not a random sample, we're just trying to determine if they are independent or not. Independent. If the parts of the sample are independent of each other. We talk about the 10% rule. Okay, and then we look at all expected counts must be at least 5. Be sure to list expected counts, and we'll do that here in just a moment. So here we go. As we're looking at this, now I'm not even going to fill in that box because we've already talked about it. So we have this, read this paragraph. This driver thinks that people in Arizona opt for a lighter color car for the hope that it reflects some of the heat. They see the distribution of cars in Oro Valley is different from the ones in the car colors across North America. She does a random sample of 300 cars. Okay, so I'm going down here to my conditions, a random sample of 300 cars. And then that shows the distribution of her sample. There's 300 cars. And the question is, do these data provide convincing evidence that the distribution of car color in Oro Valley differs from the North American distribution? Okay, well, you just saw this is our observed. We talked about that. Now we have to find the expected. To find the expected, we find out of 300 cars, we find these percents of that. Well, you just multiply 300 times the decimal of each of these. 300 times 0.23 is 69. 18% is 54. 16% is 64. 15%, I'm sorry, that's not true. That's 48. That's 48. 15% is 45. 10% is 30. 9% of 300 is 27. 2% is 6, which matches that one. 27 is close to that one. And then 7% of other is 21. So this is our expected numbers. And so I've put those numbers into my calculator here in L3 and L4. There are my observed. These are my expected. Okay. The first one's always the observed. The second one's expected. And we always list our expected as we have here. Okay. So we know that our alpha level is going to be 0.05. And our hypothesis is this. The null is simply a statement of the distribution of car color, and I'm abbreviating a lot here for space, in Oro Valley. Now this is my null. This is my alternative. So is the same as the distribution in North America. Okay, that's my alternative. My null hypothesis. This is my alternative right here. I'm just going to write that the distribution of car color differs from the North American distribution. Okay, these two are always the opposite of each other, and they're always sentences. Okay, the name of the procedure is a chi-squared goodness of fit, and I'm going to abbreviate this every single time I can. And we know that 300, let's finish this, is less than 10% of all cars. And our expected counts. All of our counts here, 69, 54, 48, 45, 30, 27, 6, and 21, all the expected counts are greater than or equal to 5. Okay, we're not going to do a picture. My specific formula is chi-squared equals the sum of the observed minus the expected squared over the expected. And so here we go. We're going to have the probability that chi-squared is, let's see, we think this number is going to be different. So we think that our chi-squared is probably going to be greater than whatever our number is going to find here. So we find this on the calculator by running, go stat. You may want to write this down, stat, test, and then going to D. Okay, we're using L3 and L4. There's 7 degrees of freedom. Did I say? I did not say that already. I'm going to write that right here. Degree of freedom is 7. And then we put our numbers in here and we calculate. Okay, there's my chi-squared, 29.92. So I'm going to say this is 29.92. And that equals 9.8 times 10 to the negative fifth. So move my decimal 5 places to the left, and I get this. My chi-squared again, this is 0.000098. Chi-squared is 29.92. My p-value is 0.0009. Whoops, one more 0. 98. Okay, we will, with a low p-value, compared to alpha, we reject the null. There is strong evidence. What is there strong evidence of? The distribution of car color in Oro Valley differs from the North American distribution. In Oro Valley is, ignoring all this, is different than North America distribution. And that is that. Hope that helps. Oops, sorry, you can't see that, can you? There it is. Okay, with a low p-value compared to alpha, we reject the null. There's strong evidence the distribution of car color in Oro Valley is different than North American distribution. And that is that.